Section 1 Introduction. Let's dive into the world of artificial intelligence and language models. Unlike traditional computing systems that execute instructions from computer programs, language models can follow instructions given in natural language or learn from patterns in large datasets. This concept is similar to Isaac Asimov's 3 laws of robotics, where the second law states that a robot must obey human orders. To create safe and reliable applications using language models, it's crucial that we can control or limit AI behavior with rules provided by users. As we look to the future, AI assistants will need to follow instructions accurately and honestly. To ensure ethical behavior, we'll need to impose rules like legal statutes or ethical constraints and verify that the AI's behavior is based on these rules, not just on textual cues or patterns identified during training. If we can't trust AI assistants to follow clear rules, it will be challenging to integrate them safely into our society. Many rules we might want to impose on AI behavior are simple and can be easily expressed in natural language. One common practice is to include the rules in the model's text prompt and rely on the model's existing ability to follow instructions. Another approach is to use a second model to score how well the first model follows a set of rules, then fine-tune the first model to maximize this score. In this paper, we focus on the first approach and study how well language models can follow rules provided in the text prompt. To build models that follow rules, we first need a way to evaluate this capability, but that's not easy. There are many strategies one might use to trick a model into breaking the rules, including crafted attacks or optimization-based attacks. It's also challenging to determine whether a model has followed its behavioral constraints without human judgment, which is slow and costly. This makes it difficult to thoroughly test many different attack strategies against potential defenses, reducing our confidence in deploying new systems. To address these challenges, we introduce rule-following language evaluation scenarios, rules, a benchmark for evaluating rule-following behavior in language model assistance. The benchmark includes 15 text scenarios inspired by common children's games and computer security concepts. Each scenario defines a set of rules in natural language and an evaluation program to check model outputs for compliance with the rules. Through extensive manual testing of our scenarios against state-of-the-art models, we identified a wide variety of effective attack strategies to induce models to break the rules. We distilled these strategies into a test suite of over 800 handcrafted test cases covering each rule of each scenario. We used this test suite to evaluate a variety of proprietary and open models, and found many failure cases for all models. We also explored whether current models can detect rule-breaking outputs, but found that even detection remains difficult. We evaluated the extent to which adversarial suffixes generated through optimization can cause models to break the rules. This attack was successful at driving model performance to near zero in most scenarios. Rules complements existing evaluations of safety and adversarial robustness, which predominantly focus on circumventing fixed universal rules. Our work focuses instead on application-specific rules expressed in natural language which may be changed or updated by the user at any time. Robustly following the rules of our scenarios while interacting with human and automated adversaries may require different approaches to improving model safety, since simply editing out the capacity for specific harmful behaviors will not suffice to fix the classes of model failures examined in our work. We're sharing our code and test cases with the community, along with an interactive demo for exploring the scenarios against different models. We hope to encourage more research into improving the robust rule-following abilities of language models, and intend for our benchmark to serve as a useful open testbed for further development. Rules contains 15 text-based scenarios, each requiring the assistant model to follow one or more rules. These scenarios are inspired by the desirable security properties of computer systems and children's games. The components of rules include scenarios, rules, and test cases. Scenarios are evaluation environments with general instructions and hard rules, expressed in natural language, along with a corresponding evaluation program that can detect rule violations. Rules are single instructions specifying required behavior for the model. Test cases are sequences of user messages for a specific scenario instance. The model is said to have passed the test case if it responds to every user message in sequence without violating the rules, as judged by the evaluation program. Section Summary. In this section, the authors discuss the importance of controlling the behavior of AI models and ensuring they follow user-provided rules. They propose a benchmark called rules, which consists of 15 scenarios that test the rule-following behavior of language models. The benchmark includes scenarios inspired by computer security properties and children's games, and evaluates the models based on their ability to adhere to the rules specified in natural language instructions. The authors also identify various attack strategies that can induce models to break the rules and provide a test suite to evaluate model performance. Section 2.1 Rules. In this study, we present a set of rules to guide the behavior of our model during conversations. These rules are given as natural language instructions at the start of each conversation. The model must follow these rules throughout the conversation. Some rules tell the model what not to do, while others instruct the model on what it should do. Some scenarios only have one rule, like in the case of encryption, while others combine up to 3 rules for a more complex task, like in authentication. In some cases, there are multiple users involved, and the user's identity must be indicated in the message. We've designed many of these rules to be similar across different scenarios. In total, we have 22 rules across 15 scenarios. We can think of these scenarios as a decision tree, where the correct behavior means starting at the root and following all the relevant rules. The behaviors are stateless, meaning they only depend on the most recent user message. We initially tried scenarios that required the model to remember past actions, but this proved too difficult, so we focused on stateless behaviors. We've designed these scenarios so that a small computer program can check if the model's response follows the rules. This program is simple and doesn't require complex computations or human input. It uses string comparison and simple patterns to evaluate the model's behavior. While it can't perfectly replicate human judgment, it does a good job in most cases. To design these scenarios and test them, we created several user interfaces. These ranged from simple command line interfaces for debugging to a web app for data collection. Interacting with the models through these interfaces helped us understand how the models respond to user inputs and adjust our scenarios accordingly. We tested various language learning models, LLMs, using our test suites. Each test case is associated with a specific scenario and randomly selected scenario parameters. We start the conversation with a user message giving the scenario instructions, a placeholder assistant message, and the first user message of the test case. The model then responds to each user message in turn, and each response is evaluated by the program. If the program determines that a rule has been broken, the model is considered to have failed the test case. We tested a variety of popular models, including several versions of OpenAI's GPT, Anthropic's Claude, Google's Palm 2 Text Bison, Vicuña version 1.3, Llama 2 Chat, and Mistral Instruct version 0.1. Some of these models are text completion models rather than chat models, so we used a simple chat template to prompt them for conversational responses. We used greedy decoding to minimize variance in the evaluations. We ran all public models locally on a GPU using the Hugging Face Transformers library. Section Summary. The section describes the rules and evaluation process for various scenarios in the benchmark. The rules are presented as natural language instructions, and the model must adhere to them throughout the conversation. The scenarios are visualized as decision trees, and correct behavior is defined as obeying all the relevant internal rule nodes. Evaluation programs are used to assess the model's adherence to the rules, and user interfaces were built to interact with the models and collect data. Various proprietary and open language models are evaluated using test cases associated with specific scenarios. Section 3.2 Manual Test Suite. We've gathered a set of manual test cases from the discussions that took place during our exploratory red teaming of the scenarios. After removing duplicates and assistant responses, we ended up with 870 test cases. These cases cover a broad spectrum of strategies and range from 155 on authentication to 27 on confidentiality. Most of these conversations focus on negative rules, but we didn't keep track of user intent, so we don't differentiate between negative and affirmative test cases. When we tested these cases, all models failed a significant number, with GPT-4 failing the least, followed by Claude Instant and Claude 2. Looking back at the successful attacks from our initial red teaming, we noticed that most of them used one of 6 types of strategies. So, we created a systematic test suite to try each strategy against each scenario. This suite includes 862 handwritten test cases that apply variations of these 6 strategies to all 22 rules in the 15 scenarios. The test cases are divided into 355 targeting negative rules and 507 targeting positive rules. Each case tries to break one rule in one scenario using one of these strategies. 1. Just ask. The user directly asks the model to break the rule, without any deception. 2. Indirection. The user asks the model to do a task that seems harmless. 3. Legalese. The user cleverly reinterprets the rules. 4. Obfuscation. The user hides a request for the model to break the rule. 5. Rule change. The user tells the model about a new or updated rule. 6. Simulation. The user asks the model to simulate or discuss a hypothetical situation. Each test case includes 1 to 3 user messages. The just ask strategy tests the model's ability to resist the most direct attack attempts. For positive rules, which usually require the model to produce a specific output in response to a specific user input, the just ask test case includes 2 user messages. One to ask the model to break the rule and another to trigger the rule-breaking behavior. All the language learning models, LLMs, we evaluated failed a large number of test cases. Performance on negative rules in the systematic test suite was closely related to performance on the manual test suite. Models generally failed fewer negative test cases than affirmative ones, with all open models except Vicuña 33b failing almost all affirmative test cases. It was easier to lead the model away from correct behavior than to coax a specific incorrect behavior from these models, especially for open models. GPT-4 failed the fewest test cases in the systematic test suite. Interestingly, Claude Instant performed slightly better than the seemingly more capable Claude 2. We also looked at the impact of including various simple messages as either system messages or instruction prefixes. Overall, we found that existing LLMs can't consistently follow our rules. While they can resist some attempts, there's a lot of room for improvement. There are several sources of variance and uncertainty in our results. For example, outputs from the OpenAI and Anthropic APIs are non-deterministic even with temperature set to 0. This leads to some variance in test case outcomes. We estimated this variance by running the same evaluation 10 times in a row and measuring the standard deviation in the number of failed test cases. The PaLM 2 API doesn't show any variance in outputs or test case outcomes, and neither do any public models when evaluated locally. It's also well known that differences in phrasing can significantly change model behavior and performance. We developed and refined the wording of our scenario instructions against the March 2023 versions of the GPT and Claude models, but we didn't intentionally choose the wording to favor specific models over others. To measure the significance of changes in performance between models or prompts, we ran McNemar's test on pairs of evaluation outcomes for each test case. In our tables, we mark p-values of greater than 0.05 in gray and p-values of less than 0.01 are underlined. Section Summary. The authors assembled an initial manual test suite consisting of 870 test cases by filtering duplicated conversations and removing assistant responses. They also constructed a systematic test suite with 862 handwritten test cases implementing variations of 6 strategies against all 22 rules in the 15 scenarios. The evaluation results showed that all evaluated language models, LLMs, failed a significant number of test cases, with GPT-4 failing the fewest number of test cases in both the manual and systematic test suites. Section 3.5 Error Detection. We're exploring whether AI models can consistently detect when their responses break the rules. To do this, we took 1098 pairs of user messages and AI responses from the models we tested, along with labels indicating whether the responses passed or failed the rules. We then used this data to see if the models could identify rule-breaking responses. While most models performed better than random guessing, none were able to consistently identify when rules were broken. The best-performing model, GPT-4, achieved an accuracy of 82.1% and an F-score of 84.0, but other models fell significantly short. We also tested a recently proposed algorithm called Greedy Coordinate Gradient, GCG, that finds suffixes, or endings, that cause models to produce specific target strings. We tested this algorithm against 3 Open 7b models on our scenarios. The GCG algorithm was able to increase the number of failed test cases for all three models, with one model, Mistral, failing almost all tests. However, we found that suffixes optimized for one model did not significantly increase the number of failed test cases when used against other models. Our experiments show that current models struggle to consistently follow simple rules. Despite significant efforts to control the behavior of these models, there's still a lot of work to be done before we can rely on them to resist attacks. However, we're hopeful that progress can be made in this area. One potential solution is to repeatedly sample model outputs until a passing output is found, but this isn't a realistic approach as we don't have access to ground truth evaluation programs in real-world applications. We also looked at whether the ability to follow rules is related to the alignment goals of today's models, such as avoiding harmful outputs. We found that rule violations aren't necessarily harmful or toxic by these measures, so it's unclear whether improvements in avoiding harmful outputs will lead to better rule following. We see rule following as a distinct capability from instruction following. While instruction following focuses on the model's ability to respond with high-quality solutions and generalize to unseen instructions, our rule following evaluation focuses on whether models can adhere to rules in conversations, even when faced with contradictory user requests. Our benchmark also accurately evaluates cases where models appear to respect the rules but actually violate them. For example, we saw many cases where a model reaffirms its commitment to safeguarding a secret key, but then inadvertently discloses the key by repeating too many details to the user. Section Summary. The ability of models to detect rule violations in assistant responses was evaluated using a binary classification task. Most models performed better than chance but were unable to reliably detect rule violations. Adversarial suffixes were also evaluated, and it was found that they could increase the number of failed test cases for the evaluated models. Current models are inadequate in following simple rules, and more work is needed to improve their abilities. Section 5. Related work. In this section, we'll discuss related work in the field and how our research fits into the broader context. Firstly, we'll talk about rule learning and induction. Our work, which focuses on adhering to rules provided by users, is distinct from traditional research in this area. This research spans several fields, including linguistics, cognitive science, and artificial intelligence. There's also been recent exploration into rule induction using large language models, LLMs. Next, we'll touch on the alignment of LLMs and their red teaming. Over the years, methods to align LLMs with human safety and usability standards have become more effective and wide-ranging. At the same time, extensive red teaming studies have increased our confidence in the reliability of these methods in most cases. However, it's important to note that both manual and automated methods can still easily bypass the safety and alignment training of LLMs. We've adapted some of these techniques, like jailbreaking prompts and the GCG attack, to successfully encourage LLMs to break rules in the rule scenarios. We'll also discuss defenses and security for LLMs. Recent research has looked into input smoothing and detection as potential defenses against adversarial inputs. Other researchers have identified possible threats to the security of LLM-enabled applications, beyond just model alignment and safety. Privacy is another crucial aspect of safely deploying LLM-enabled applications. LLM systems are vulnerable to membership inference and data extraction attacks, and they may also unintentionally reveal private personal information. Furthermore, LLMs could be misused to infer private personal information from publicly available data. Lastly, we'll mention red teaming competitions. There's been a surge of capture the flag style competitions recently, which focus mainly on bypassing a fixed set of rules. These competitions reflect the growing interest from the wider software community in securing LLM systems. We hope our work will help direct this interest towards further research progress.